In this lesson, we're going to be solving systems of linear equations by elimination. And to make that happen, we're always going to look to try to cancel a variable. There's a couple of things that we're going to do to make that happen. We are going to manipulate one or both of our equations, and then we're going to combine them, all trying to get a variable to cancel. So let's see how that works. So our first equation, directions are going to say solve the system. And we'll start off with an x plus y equals 3 and x minus y equals 5. So we're going to try and solve this system of equations. And one thing that we're going to try and make sure happens every time with this is we're going to try to line up everything. We're going to put them in standard form, this linear equation. So we're going to put the x's and the y's on one side, x's first, y's second, line up our equal signs, line up our constants. And we're going to try to figure out, without graphing, what this may look like. Would the lines, if we graphed them, would they intersect each other? Would they be parallel? Or would they be the same line? So, elimination is we're looking for this exact situation to happen. When we're going to combine our equations, which basically means we're going to combine the like terms from both of the equations. So, when that happens on this one, this is the ideal situation, and we're going to try to make this happen on other equations. The y values are exact opposites of each other, which when you combine them, they cancel. So, perfect. So we'll combine our x's together, that'll get us 2x. We combine our constants together, and that'll get us 8. We'll try to get x by itself, and so we'll have x is going to equal 4. So if x equals 4, we'll go back to the original, pick one of the two originals, and substitute the 4 back in, see what our y value is. I like the top one because it's a positive y. Wouldn't matter if you use the bottom one, you're still going to get the exact same result because it's the same coordinate that's going to satisfy both equations. So we'll take the top one. X value is 4 plus the y value needs to equal 3. So we're going to find that y value. We'll subtract 4 on both sides, so the y will equal -1. So we think that 4, -1 is the solution. So if you graph them, this is where they would cross. If you plug them into both, it should satisfy both equations. So we're going to verify that right now. So we're going to check it by taking this 4, -1, and we just use this top equation to create our y value, or to find our y value. We're going to verify that it works then for the other equation. We could do both, but it's most likely going to work for the top one. We really need to verify that it works for the other one that we just didn't use. So our x value is 4. Our y value is -1. And if we do this right, if our coordinate is right, this should add up to 5. So subtracting a negative is the same as adding a positive. So that adds up to 5. So it checks. Alright, so let's see another one. So our second equation, 5x plus 2y equals 9, and 3x minus y equals 1. So we have a similar situation that we had before, where the y values will almost cancel each other. But this is where the manipulation thing happens. Just like here, where we divided both sides of the equation by 2, we could also go the other direction with that. And we could multiply both sides of the equation by something. And in particular, we're going to multiply this equation, both sides, by 2. To do that, the reason that we would do that is when we distribute this in, you'll get a 6x minus 2y equals 2. And now we'll rewrite the other equation, the first equation. We didn't do anything to it. Now the y values cancel perfectly. So just like dividing both sides of an equation by something, we can always multiply both sides of the equation by something. Just make sure you distribute this into every single term. Don't forget about your constant. So this time the y values canceled again. Great. And we will combine our like terms. So it makes 11x equals 11. We'll divide by 11. So our x value is equal to 1. So now let's go back, and we'll pick one of the two equations to substitute our x in. Maybe the bottom one, it won't really matter. So 3 times 1 minus y equals 1. So let's try and find out what y is. 3 times 1 is 3, minus 1, y equals 1. Subtract 3 to the other side, so negative y equals negative 2. Divide both sides by negative 1. Y equals positive 2. So we believe the answer to be 1, 2. So let's find out if it's true. So we just used the bottom equation to find this coordinate. Let's verify it with the top equation. So 5 times our x value of 1 plus 2 times our y value of 2 is supposed to add up to 9. This multiplies to 5, this multiplies to 4, and that is going to add up and satisfy the equation like it's supposed to. So let's make our answer stand out. Should have done that with this one. So if we were to graph both of these two lines from this system and from this system, they would intersect each other. And they would intersect, this one would intersect at 4, negative 1. This would intersect at 1, 2. So let's try another. So if we have x plus y equals 3 and negative 2x minus 2y equals negative 8. So we're trying to cancel out a variable. Let's say we'll try to cancel out x's this time. So if this is a negative 2x, maybe we can make this a positive 2x. To do that, we would distribute a positive 2 in to every single piece. So that would give us 2x plus 2y equals 6. We'll rewrite the original second equation. We didn't do anything to it. And we are ready to combine our like terms, and we were shooting to cancel our x's, which they do. But at the same time, we didn't mean to, but we accidentally canceled, not accidentally, we canceled our y values at the same time. So that gives us a 0 equals negative 2. So we lost all of our variables. If you lose all your variables, that's the special case. We're either going to get no solution or an infinite solution. They're either going to be parallel to each other or they're going to be the exact same line. So 0 equals negative 2. This is kind of the way I think about it is, does 0 equal negative 2? No. So that's no solution. So if we were to graph those lines would be parallel to one another. They wouldn't cross, they don't have anything in common, so there's no coordinate that would satisfy both equations. All right, so let's do another. So number 4. We'll take 2x minus 3y equals 2. 3x minus 5y equals 4. So we're trying to cancel out a variable, and either we're going to cancel our x's or cancel our y's. So if we look at our x's, between a 2 and a 3, they both can become a 6. Between our y's, the 3 and the 5 can both become 15. So maybe we'll shoot for the x's just because it's a little bit smaller. Now, not only can they become 6, but one needs to be negative so that way they'll cancel. So we'll distribute maybe the negative to the top one. Does not matter. And we'll distribute a 2 to the bottom one. So that's going to get us a negative 6x plus 9y equals negative 6. So that's distributed to every single piece. Here we're just doubling every single piece. So 6x minus 10y is going to equal 8. And now we're ready to combine. And what should be happening at this point is that our x's should be canceling each other, which is perfect. They do. So let's combine our y's. We get a negative y equals 2. Divide by negative 1. Y equals negative 2. So we have our y. Let's find our x. Go back to your original because the numbers are going to be smaller than what we did here. So go back to the original. Maybe we'll take the top equation. Does not matter. 2x minus 3 times our y value of negative 2 needs to equal 2. So negative 3 and negative 2 becomes a positive 6 when you multiply them together. And And we will look to solve this. Subtract 6. 2x equals negative 4. Divide by 2. X equals negative 2. So we believe our solution to be a negative 2, negative 2. So let's check to verify that it works. So our check. We just use the top equation to get our solution, to finish off to get our x value. So let's verify that it works for the bottom equation. So 3 times negative 2 minus 5 times negative 2, the x and the y are the same. Let's see if it adds up to 4. So that's a negative 6. Negative and a negative makes a positive 10. Does that add up to 4? Yes. So negative 2 and negative 2 is our solution. So if we graphed them, they would intersect at negative 2, negative 2. One last. Our last equation is going to be 2x minus 3y equals 5, similar to that one, and negative 6x plus 9y equals negative 15. So same as before, I'm looking at the x's pretty nicely that this can definitely become a 6. We already have a negative on that one. It's great. So I'll multiply it by 3. So our new equation will be 6x minus 9y equals 15 after we distribute the 3 to every single piece. I'll rewrite, we didn't do anything to this equation, so we'll just rewrite that. And we are ready to combine our like terms. X's go away. Y's actually go away as well. Didn't mean for that to happen, just happened. That's okay. So we have a 0 equals. So again, once we lose our variables, that's when we're going to get a no solution or an infinite solution. And the constants go away as well. So we get a 0 equals 0. Everything canceled. That is an infinite solution. It's because they are exactly the same line. This equation and the second equation is a perfect multiple of this equation. If you take every single piece on this equation and multiply it by a negative 3, you would get the exact same equation as this one. So they're perfect multiples, which basically means that they're the same line. So infinite solutions is not quite enough. So it's infinite solutions of, it can't just be any random solutions, it has to be solutions of these. So as long as it works for one, it's going to work for the other. So infinite solutions of 2x minus 3y equals 5. We'll just grab one of the equations. So as long as it works for this, it's going to work for the other one as well. And that is solving systems of linear equations by elimination.